Welcome to RF transceiver design course. In last few classes, we have discussed about the oscillator. Now, one of the important design component for RF transceiver is a power amplifier. So, we will try to discuss the power amplifier design in upcoming lectures. So, we already have seen while discussing the transceiver architecture that how the power amplifier is important for transmitter design. So, as we have discussed for receiver low noise amplifier design, similarly for transmitter power amplifier design is important. You can use all the methodology that we have used to design a power amplifier, that we have used to design a low noise amplifier. However, there are certain parameters which are important for a power amplifier design. So, if we want to see the power amplifier specification, there are various specifications that has been listed out here. That one of the specification important for power amplifier is a gain and gain flatness. What it means that for all entire bandwidth of the operation, the gain should be flat because we are going to give the modulated signal to the power amplifier. So, for that you should have a gain with the flatness in for entire band. Second is the power consumption. Uh, Power amplifier is a power hungry component and it is increasing the power. It required higher power for the higher efficiency. So, power consumption is also important parameter. Third is the linearity. As we have discussed during the initial lectures that there are certain modulation scheme which has a amplitude modulation which involve the amplitude modulation, and if we want to recover the transmitted signal then the power amplifier should be linear, and we already discussed the OFDM modulation, and for that peak to average power ratio is also important. So, power amplifier linearity is important. Its signal peak to mean ratio is also important because uh, because of the modulation scheme that we are using. Then important parameter is the bandwidth. You should have a sufficient bandwidth in your power amplifier, so that because we are transmitting high bandwidth signal to the antenna through the antenna, and that power amplifier also should ensure the sufficient bandwidth. Frequency band for transmit and receive, there are different frequency band that we are using, because high power signal will feed through to the receiver. So, frequency band is also important, what band we are working. Then how much power is delivered to the antenna is also important for power amplifier. And another important parameter is the permissible in band emission and permissible out of band emission, because we have a power amplifier which is going to transmit the signal in the in band. However, some of the frequency component of other harmonics will also generate out of band emission. So, that is also important, that how much power is permissible in the band or out of band, that we should know prior to the design of the power amplifier. Stability over the voltage standing wave ratio. So, stability is also important parameter for power amplifier, because if it go to instability, then there is a possibility that the device or circuit that we are using might burn, because very high power is involved. Ability to transmit into unknown and varying load efficiency. So, it should have a because the power amplifier is connected to the antenna. So, that antenna might have a different load condition, and in your power amplifier should work, it should have ability to transmit into unknown and a varying load efficiency. Minimizing any loss in the form of heat and noise, that is also important for power amplifier, and we should find the minimum size as much as possible. So while finding out the size of the device or size of the power amplifier, we can have a minimum size, then it is a better. So these are the uh, parameters which are not there are many more parameters that is also possible, but these are the parameters that I think is important for power amplifier design. And no doubt efficiency is also part of this. So it should have a sufficient efficiency for entire frequency range, and so that the power loss, the DC power loss, will be minimized. So mostly for power amplifier, linearity and this efficiency are more targeted parameter, and other will be the part of the same. So for this presentation, if we see, if I will outline, we will try to see the basic class of the amplifier, class A, class B, class C, and if we try to improve the high efficiency of power amplifier, what are the different kind of efficiency that we will see. uh, Class A, if we want to improve the efficiency, class E and class F. There are certain example we can try to address, that is a cascode power amplifier, positive feedback power amplifier, power amplifier with a power combining, and polar modulation can also be used in power amplifiers. Various linearization techniques, because linearity is important. So two things that we mostly target: linearity and efficiency. So on efficiency, there are on basis of efficiency, there are various class has been defined, class A, B, C, and on the linearization technique, there are various linearization techniques like feed forward, Cartesian feedback, pre distortion, polar modulation, out phasing, and Doherty PS. So these are the various linearization techniques we will try to address. So before going into the class of the PA, some of the issues while designing on chip power amplifier that we will discuss. The first issue or general consideration, that there is a trade-off between the output power and the voltage swing. So what it says, that if I want to transmit a 1 watt of power, if I want to transmit a 1 watt of power, and if that 1 watt of power, if we try to convert into dBm, it will be 30 dBm for 50 ohm load. So for this much power, you require a supply voltage, peak to peak voltage should be around 20 volt, and your load peak current is around 200 milliampere. So this if we try to use the common source amplifier with a RL load, or if we have a common source amplifier biased through the current source and this is a RL load, then what you require is your peak to peak voltage requirement is too high. So in order to deliver that much power, now that what will happen, that voltage is across the that is a drain voltage which is a 20 volt and very high. So one solution we can think that we can put an inductor here, and that inductor will increase the swing 2 times at here, that is a 2 VDD. Still your M1 transistor is experiencing a 20 volt, and what is happening that in order to deliver that much power you require a very high voltage swing. So, there is a trade-off that because in the MOSFET we have a limited voltage swing due to the uh, limitation in the VDD. So, this output power and voltage always has a limited uh, i- it has a limited voltage swing and you want to deliver the high output power. So, if we want to deliver, so here the same thing has been written whatever I discussed. If the load is realized as an inductor, the drain AC voltage exceeds VDD, it will even reach to 2 VDD, but the maximum drain source voltage experienced by M1 is still 20 volt. So, uh, in certain literature it has been proved that the product of breakdown voltage and FT of silicon device is around 200 gigahertz into volt, 200 gigahertz volt. So, that will limit the voltage swing and output power. So, what is the solution? So, the solution is incorporating the interposing a matching network. So, in order to reduce the peak voltage experienced by the output transistor, a matching network is interposed between the PA and the load. So, what will happen, this network transform the load resistance to a lower value, that is RT. So, this RL at this point will be transferred to the RT, which is a low resistance, so that the smaller voltage swing still deliver the required output power. So, you do not need a very high voltage swing. So, we will try to take one example for that. The above PA, if it want to deliver 1 watt of power RL with supply voltage of 1 volt, because here supply voltage is 1 volt, what we need to do is find the value of RT. So, here the peak to peak voltage swing VPP at the drain of M1 is approximately equal to 2 volt, because it is peak to peak voltage swing that we are thinking. So, your P out, which is equal to half V peak to peak by 2 square into 1 by RT. Now, what we want to deliver is a 1 volt and V peak to peak is also fixed. So, what is the value of RT? 2 by 2 is 1. So, RT is nothing but a 1 by 2. So, we need to have a half ohm, means 0.5 ohm resistance at this place. If you try to see 0.5 ohm resistance and that RL is a 50 ohm. So, if we want to convert 0.5 to 50, that should experience, and if the voltage swing is double, then your requirement is a 1 by 10 ratio of the transformer. So, what will happen? The matching network must therefore transform RL down by a factor of 100, and figure above shows an example where is a lossless transformer having a turn ratio 110 converts a 2 volt peak to peak swing at the drain of M1 to 20 volt peak to peak swing across the RL. So, the here the requirement is a matching network. We should have a matching network which can also help us to transform the lower voltage swing to the higher voltage swing. However, the amount of current that is experienced by the transistor is always high, and the on chip transistor should also withstand that much current. So, now the next point, that effect of the high current. Now, that much high current, if you want to if your transistor want to uh, draw that much large current, then its width of the transistor, let us say for MOSFET the W is very high, and that width, if you try to increase the width, if we increasing the width, the capacitance, that this is a output stage of the power amplifier that has higher capacitance, which the previous stage, you need a previous stage, because if there is a mixer is directly connected to the output stage or the PA, it cannot drive that much high capacitance. So, what you need is you need to introduce a driver stage in between. So, this driver stage has been introduced in between, so that it can sufficiently drive that much high capacitance. Now, the another issue that is arising in the power amplifier is package parasitics. So, if we consider the bond wire at the source side, and so in common source amplifier, this is a source which is connected to the ground, but it in the package it will have a bond wire inductance. This is a bond wire inductance. Now, this bond wire inductance, and there is a ground, and there are there are inductance, let us say one inductor here, that is a load, and when we are connecting this to the VDD at the pad, there is another inductor here. So, these inductance are parasitics, and what will happen, that that will also add the loss. So, our efficiency will reduce by due to this parasitics also, and this matching network, if we also try to, if we want to make a on chip, that will also add too much loss, because on chip inductor we already have seen inductor and transformers are lossy. So, in many case the all the matching network needs to be designed off chip, so that the loss will be reduced, and that will try to give the high power. So, that is why, and this bond wire, when we consider very high current, this all the parasitics is adding too much loss, and that is why we can make a matching network off chip, and this other stage is on chip, active components on chip, so that our losses are reduced at high currents. Now, another important parameter in the power amplifier is the efficiency. So, there are two kinds of efficiency that we can define. One is a drain efficiency or a collector efficiency for bipolar transistor, because there are many application, many power amplifier has been designed in a silicon germanium by CMOS process, which is a bipolar CMOS and widely used for a power amplifier design, because its FT is high and the power handling capability is also high. So, the efficiency, drain efficiency is given by the uh, loss PL, means power loss into the in the circuit divided by the power supply. Now, so PL is a power average power delivered to the load divided by the power supply. So, average power drawn from the supply voltage. So, the if average power delivered to the load is equal to the average power that we are drawing for supply, then our efficiency is a maximum. So, if we want to have a efficient power amplifier, then your circuit should consume as minimum power as possible, and there is no any power amplifier in which circuit is consuming no power, there is no possibility. So, that is why we cannot get a 100% efficient power amplifier, but it has a some efficiency that we can target to achieve. There is another uh, important efficiency parameter, that is the power added efficiency. So, if you have a power amplifier and there is input power P in and output power P L, there is a supply voltage, means power supplied is a P supply, then what we can get is a power added efficiency P L output power minus P in, because in last example we have seen if some of the power is provided by the uh, driver stage, that is a P in. So, P L minus P in by P supply. So, that is how much power P in already has giving the power, how much power amplifier is adding to the actual power that is received. So, that is why it is called a power added efficiency, that P L minus P in, because the actual power which is added is given by P L minus P in divided by P supply, where P in is the average input power. So, for common source stage, in many cases for low frequency, your power added efficiency is equal to drain efficiency at low or moderate frequency, because its input impedance is capacitives and hence average input power is 0. But as we are increasing the frequency, high frequency, your input port impedance has a real part in Z in, and that draws some power. So, in that case you need to consider the power added efficiency, and for stand alone mixer, power added efficiency is less than the actual drain efficiency, because you need to match input impedance with the 50 ohm, and when you are matching, your input is also drawing the power. So, this is a P L minus P in by P supply. So, this is about the efficiency and its parameter. Now, we will try to see the uh, various configuration. Before going to the various power amplifiers class, another important parameter for power amplifier is a linearity. So, how we can characterize the power amplifier? So, in power amplifier has a more important. So, power amplifier non-linearity leads to two effects. Means because of the modulation, there is a means when there is a non-linearity in the power amplifier, there is a high adjacent channel power which results in a spectral regrowth, and we already have seen how the spectral regrowth happens when we discuss the basics of the communication. And another is the amplitude modulation. So, these two uh, will, because of this amplitude compression and the spectral regrowth introduced by the power amplifier non-linearity, our power amplifier should be as linear as possible, and power amplifier linearity is directly related to the modulation scheme that we are interested in. So, non-linearity of power amplifier, if we are using amplitude modulation, it will distort our signal and it will be very difficult to recover the same signal which is transmitted. So, what it's require is that if we try to do the circuit simulation with the modulated signal, if we apply, and that will increase the timeline of the designing of the power amplifier. So, in that case your circuit simulation will take a longer time with a modulated signal. So, what is a way we can also ensure the linearity, and we make sure that it will also perform better for the modulated signal. So, that is why there is a two generic test which can be used, which is a intermodulation and compression. So, intermodulation, when two tone we will apply to the power amplifier, and then we try to see the third order component. So, IM3 component, and we define the IP3, and we also define the 1 dB compression point for the power amplifier. Now, when we see the two tone analysis, we should ensure that the output power level is 6 dB down, because when we are taking a differential output, it is its swing is going to have experience a 6 dB higher. So, we should ensure that the power level is a 6 dB down, and this in power amplifier, uh, we should not use amplifier at the 1 dB compression point. It should be used at the uh, back back of the power. So, that should be in the linear range, so that it will not express the too much compression. So, when we are try to design the power amplifier, we need to ensure the linearity by doing the testing on intermodulation and the compression. Now, we also see there are two kind of power. We can get the power amplifier with a single ended and a differential. So, if we have designed a complete transmitter which is a I and Q, in phase and quadrature component, and we have discussed while discussing the transceiver architecture that in phase and quadrature will come from the modulated signal, then we do the up conversion, and if we use a power amplifier single ended, which is required for the antenna, what will happen that it wastes half of the transmitted voltage which is coming from the other part of the up converter. So, what is the advantage of single ended PS which is mentioned? The antenna is typically single ended, and single ended RF circuits are much simpler to test than their differential counterpart. What is the drawback? Drawback number 1, that they waste half of the transmitter voltage gain, because they sense only one output of the up converter. So, what is the solution? The solution is we can introduce a balloon, we can introduce a balun in between up converter and the power amplifier. This balun, what it will do? Differential single signal to the single ended signal, it convert the differential signal to a single ended signal, and then it amplifies. So, this issue can be alleviated by interposing a balun between the up converter and the PA, but balun will also introduce a loss. If you have a single ended PA, we will see more issues. If you have a single ended PA, the another drawback, that this is a bond wire inductance at the between external VDD and internal point at the power amplifier, and bond wire at the source side. So, what will happen, that this will be, because of this inductor, very large transient current that they pull from the supply to the ground, and that LB1, there is a possibility that if this inductor is in similar value to the LD, it will change the resonance or impedance transformation properties, and there is a signal feedback at the preceding stages. LB2 degenerates the output stage and introduce a feedback. So, because it is a single ended, the common mode effect will also come at the power amplifier, and that we cannot neglect in the single ended power amplifier. So, what is the solution? We can use a differential power amplifier. Now, differential power amplifier, there is a possibility to have the, if we have a differential power amplifier, when we take a differential output, it will help to reduce the leakage, means from the external VDD. So, when we do the differential realization, less sensitive to LB1 and LB2. So, your circuit will not be that much sensitive to these two bond wire inductance, and the degeneration issue also will be relaxed. So, your power amplifier must still drive a single ended antenna in most of the cases. We do not have a differential. So, you need to introduce the balun at the output stages after the power amplifier. So, if there is a two ways, you can either use a power amplifier balun before the power amplifier and balun after the power amplifier. Now, balun after the power amplifier and before the amplifier, it will add the loss. So, if you take an example of efficiency and loss due to the balun design, if your balun has a 1.5 dB loss, if your balun has a 1.5 dB loss, and that balun, if it is introduced before, so there is a two case, before PA, like what we have seen here. If we use this, if we add before the PA, this is a PA, and if it has a loss of 1.5 dB. Now, if the preceding stage is adding around 0 dBm power, 0 dBm by up converter, then the loss in terms of heat in the balun is 0.3 milliwatt, if balun has a 1.5 dB insertion loss. If it is after the PA, and if your power amplifier is around 1 watt or 30 dBm, so by PA, power output is 30 dBm, then loss is around 300 milliwatt. So, again if we try to use a power balun after the power amplifier, there are too much loss. So, either it is better to use the power amplifier balun before the PA. If we use the balun before the PA, it will needs to be designed on chip, it has a higher loss, and after the PA, it is going to add too much loss in terms of power. So, there is a trade-off based on the requirement and the output power, we can choose that we should use before or after. We will discuss more about the power amplifier different class topology in the next class. Thank you.